Okay, welcome to the seminar. I'm delighted to introduce Gavin Ball, who will speak on of the Université du Québec à Montréal, who will speak on quadratic closed G2 structures. And let me just remind everyone that the meeting is being recorded.
Okay, thank you, Carolyn, and thanks to the organizers for inviting me to talk. I think this virtual seminar has been great. It's been one of the few good things to happen in the past couple of months. I've enjoyed it a lot. Okay, so yeah, the title of my talk is Quadratic Closed G2 Structures, and it's based on a preprint I put on the archive last month, which itself contained material that appeared in my PhD thesis. Okay, so let's get started. I want to explain a little bit what is a closed G2 structure, etc. Anna Fino in the first talk, the seminar series gave a great survey of closed G2 structures, but I'm not going to assume that everyone here attended that or remembers all the details. Okay, so we need to begin with a little bit of linear algebra that is special to 7 dimensions. So let's let V denote R7. GLV acts on the space of 3 forms with 2 open orbits, which I'm going to call lambda 3 plus and lambda 3 minus. So this is already a pretty unusual situation. It's very rare that the general linear group is going to act on one of these spaces of differential forms or spaces of tensors with open orbits. This is something that's pretty special to dimension 7. Okay, and elements of this first open orbit, lambda 3 plus, I'm going to call them definite 3 forms. Okay, an example, the kind of standard example, depending on your conventions, is this 3 form, the standard 3 form on R7, given with this. Here, E1, 2, 3 means E1 wedge, E2 wedge, E3, and E1, 2, 3, etc. are the standard basis vectors for R7. So this one is a definite 3 form. In particular, the space lambda 3 plus is just the space of all 3 forms that are GLV equivalent to this guy. Okay. Now the GLV stabilizer of any definite 3 form is isomorphic to the compact simple Lie group G2. So this is a very kind of down to earth definition of G2. It's a stabilizer of one of these kind of 3 forms that lives in one of these open orbits. It's very similar to the definition of, say, SO7 as the stabilizer of a definite bilinear form in dimension 7. Okay, now a closed G2 structure is simply a 3 form. So I take a 7 manifold M, and a closed G2 structure on M is just a closed definite 3 form. So closed just means that the exterior derivative vanishes, and definite just means that pointwise it lies in this kind of orbit lambda 3 plus. Okay. Now this is this definition should kind of maybe remind you of the definition of a symplectic structure. A symplectic structure on an even dimensional manifold is given by a closed 2 form that satisfies some nice algebraic non-degeneracy condition. So a closed G2 structure is again defined by a closed differential form satisfying some kind of algebraic non-degeneracy condition. Okay, but closed G2 structures are actually quite different from symplectic structures. So for symplectic structures, there's no local geometry. All symplectic structures are locally equivalent. But that's not the case for closed G2 structures. Closed G2 structures have local geometry associated to them. In particular, a closed G2 structure defines a Riemannian metric with an associated volume form via this formula. So U and V here are tangent vectors on M. And I take U, insert my 3 form, wedge with V, insert my 3 form, and then wedge with 3 form again. That's going to give me a 7 form. And it turns out there's a unique way to write this as G phi of U and V times vol phi. It might look like I'm defining 2 pieces of information with just 1 equation, which might seem a bit dodgy to you guys, but the key point is that the volume form is supposed to be associated to G phi, so that's kind of an extra hidden condition that fixes the scaling. Okay, and the fact it's a Riemannian metric instead of a metric with a different signature is because we've chosen this orbit for the 3 forms, this lambda 3 plus. These definite 3 forms. In fact, that's why you call them definite 3 forms, because you get a definite metric coming out of it. Okay, I'll just also say that this construction works whether the 3 form is closed or not, but I just want to focus in this talk on the case of closed G2 structures. Okay, and as an example, the standard 3 form from the previous slide just defines the usual Euclidean metric and kind of standard volume form on R7. Okay. Now, there's a particularly special class of closed G2 structures, which I think people are especially interested in, and that's the condition, that's if a closed 3 form also satisfies this extra differential condition. So recall that I had a metric and a volume form associated to my 3 form, and together these are going to define a Hodge star. So I can take the Hodge star of my 3 form, that's going to give me a 4 form, and I could ask that that be closed. Now, if that happens, phi is called torsion-free. And in this case, it takes a little bit of work to show, but it's not too bad. It turns out that the free form is actually parallel with respect to the Levi-Civita connection of the induced metric. And that implies that the holonomy group of the induced metric is contained in the Lie group G2. And then curvature identities that must be satisfied with holonomy contained in G2, for example, imply that G is Ricci flat. And conversely, if I had a metric that has its holonomy group contained in G2, then there's a unique torsion-free G2 structure phi, so that G is equal to the induced metric of phi. So in some sense, metrics with holonomy contained in G2 are kind of equivalent to torsion-free G2 structures. Okay. And these manifolds with holonomy G2 are kind of a focus of a lot of research at the moment, and have been for the past 20, 25 years. And they're interesting from lots of points of views. So they're interesting from Riemannian geometry because currently they're kind of the only source of compact Ricci flat simply connected manifolds. You can write gauge theoretical equations on them, so they're interesting from the point of view of high dimensional gauge theory. Interesting from the point of view of calibrated geometry because this 3-form phi and the 4-form star phi define calibrations on your manifold. Physicists are interested in them from the point of view of string theory. They're expected to play a role in M theory with supersymmetries. There's various other interesting parts. So that's kind of motivation for the study of these torsion-free G2 structures. And the motivation for the study of the more general closed G2 structures, I would say, primarily comes from the torsion-free case. They kind of play an auxiliary role here, as I'll explain. So the first motivation just comes from the construction of compact G2 manifolds. So right now, every known method of producing a compact manifold with holonomy G2, what you do is you start with a closed G2 structure so that this 5-form D star phi is kind of small in the appropriate sense, so an appropriate norm. And then there's a result of Joyce that says when this thing is small in the correct appropriate sense, then you can kind of perturb it to a nearby torsion-free G2 structure in the same cohomology class as phi. Because for a torsion G2 structure, you want this thing to vanish. So, you know, if it's small, it's kind of very close to vanishing. And, you know, this result guarantees that you can perturb it. And it's interesting, it lies in the same cohomology class as phi. The second motivation comes from geometric flow that you can write down for G2 structures. So the Laplacian flow evolves a G2 structure by this equation. So the G2 structure should evolve in the direction of its Laplacian, where the Laplacian is taken with respect to the metric and orientation defined by the 3-form itself. Now this closed condition is preserved by this flow, which is nice. And it's kind of hoped that if you start with an initial closed G2 structure and run the flow, okay, it's almost certain to have singularities, etc. But maybe after some surgery or some other operations that you could do on this, you might be able to produce a torsion-free G2 structure in the limit within the same cohomology class. And I guess the kind of reason that this is hoped is because of Joyce's result. So this Laplacian flow would kind of give like a parabolic approach to this thing. There's a lot to be done here. There've been good results, but I think the understanding of the long-term behavior of this flow is just not there. So I'd like to emphasize that this kind of statement is very vague and may end up being naive. But in both cases, the closed G2 structure kind of functions as like an initial condition that you then want to do something to get a torsion-free G2 structure, by doing something, perturbing it. Okay, so understanding closed G2 structures, the better you understand them, maybe the better you can understand torsion-free G2 structures. Okay, so let's talk a little bit about kind of the basics of closed G2 structures. So we said it was torsion-free if this 5-form vanished. Well, if it's not torsion-free, it will have some torsion. And generally speaking, this 5-form is equal to tau wedge phi, where tau is some 2-form that you call the torsion form of phi. So for a closed G2 structure, you can associate this 2-form. And it satisfies this special algebraic condition that tau wedge the 4-form should vanish. And this kind of implies that tau is a section of a particular subbundle of the space of 2 forms. And that's a subbundle that's modeled on the Lie algebra G2. So I can, by lowering an index, think of G2, which would usually sit inside GLV. I can lower it. It has to lie in SO7 because we know that G2 preserves the metric. So it lies in lambda 2 of V star, which I identified with SO7. And then this algebraic condition says it actually lives in G2, this G2 space, this 14-dimensional space that's a subset of this. Okay. And this torsion 2 form is kind of the basic first order invariant of a closed G2 structure. So kind of, it's a first order invariant because I get it by differentiating my structure once. So before I take the exterior derivative here, all this information is just algebraic. You would get it from phi, from the G2 structure, by doing algebraic operations. And then I take a derivative, I've taken one derivative, and I get the torsion form. So it's a first order invariant. And it's kind of, in some sense, the only first order invariant. Okay, and interestingly, it determines the Ricci tensor of the induced metric by a formula due to Robert Bryant. So the Ricci tensor can be expressed in terms of tau and the exterior derivative of tau. And again, that makes a little bit of sense because tau is first order, d tau you differentiate once more, it's a second order term, and the Ricci tensor of the metric should be second order as well. Okay, and in this formula, we have a 3 form here, and there's a certain G2 equivariant linear map, which I'm not going to go into the details of, that will send a 3 form to a symmetric tensor. Here. Okay, one interesting consequence of this formula is that you can trace both sides and do some algebra, and you find actually that the scalar curvature of the induced metric is equal to -1/2 times the norm of tau squared. So that's interesting for a couple of reasons. First off, the scalar curvature a priori looks like it should be a second order invariant, but actually it's expressed in terms of first order information. And the next interesting thing is that the scalar curvature of the induced metric then is always non-positive. And it's going to be 0 if and only if tau vanishes, so if and only if we're in this torsion-free case. Okay, so we already see that there's kind of an interesting interplay between the geometry of the G2 structure, this torsion form, and the geometry of the induced metric, G phi. And it's kind of not obvious, you know. I personally don't really have much intuition for this formula. You just have to do the calculation and see what happens. Okay, so now the title of the talk is Quadratic Closed G2 Structures. So I'd like to explain what are these quadratic closed G2 structures. So let lambda be some constant, some real number. A closed G2 structure phi is called lambda quadratic if it satisfies this equation. So if its torsion form tau satisfies this equation that prescribes the exterior derivative of d tau. And you see here that the constant lambda is a parameter that appears in the equation. Okay, this condition was introduced by Robert Bryant as kind of the most general way in which this 3 form d tau could be possibly written quadratically in terms of the components of tau. You see that everything on the right-hand side here is a quadratic function of the components of tau. The sort of, what this is saying is that this equation makes good sense from a representation theoretical point of view. And it kind of, it captures kind of, it's a general enough equation. The presence of this parameter lambda means it's a general enough equation to capture all the possibilities and this family of equations. Okay, now let's analyze this equation a little bit deeper. So on a manifold with G2 structure, the space of 3 forms splits as a representation kind of G2 into a 1-dimensional piece, a 7-dimensional piece, and a 27-dimensional piece. Okay, so we can look at d tau that's specified by this equation and look at which piece does each term belong to. So this term belongs to the 1-dimensional piece. The 1-dimensional piece is spanned by the 3 form, and this is just a multiple of the 3 form. And this term belongs to this 27-dimensional piece. It just turns out that because of the algebraic symmetries that tau must satisfy, then this particular combination must lie in this 27-dimensional piece. And furthermore, this 0 lies in lambda 3/7 of n. Now, what I wanted to highlight was that for any closed G2 structure, not just one that satisfies this lambda quadratic equation, these pieces are always specified. They always have to be this. So the 1-dimensional piece of d tau for any closed G2 structure is always 1/7 norm tau squared times phi, and the 7-dimensional piece always vanishes. So the new information in this equation is prescribing the 27-dimensional piece of d tau. So in some sense, this equation is 27 equations. You know, it's specifying 27 equations. Okay, now it's very nice just to write down this kind of arbitrary equation and say it's kind of the most general way in which the 3 form can be written quadratically. But you'd hope that maybe there are some kind of interesting special cases depending on the constant. So that's true. There are several special values of lambda that are of particular interest. So for lambda equals 1/2, so this half quadratic condition, it's exactly equivalent to the Einstein condition for the metric G phi. Remember, we had this formula for the Ricci tensor. And if you substitute the quadratic equation, which prescribes d tau, into this, you'll find that the metric is Einstein, so the only thing that appears would be the scalar curvature. Now there's a kind of interesting inequality for closed G2-structures on compact manifolds that Robert Bryant proved, which is kind of a pinching inequality on the Ricci tensor. So what it says is that the integral of the norm squared of the traceless Ricci tensor must always be larger than this particular multiple of the norms of the square of the scalar curvature. So in particular, you couldn't have a closed G2-structure on a compact manifold that satisfied this Einstein equation without it being Ricci flat and therefore torsion free. Because otherwise, well, if it's Einstein, then this left-hand side vanishes, which would imply that the right-hand side vanishes because it's positive. And remember, the scalar curvature vanishing implies that the structure is torsion free. So there's this nice pinching inequality due to Robert Bryant. And it turns out the equality in this formula holds if and only if phi is lambda quadratic with lambda equals to 1/6. And that's interesting again, because this is an inequality involving global quantities, these integrals over m, whereas the quadratic condition is a kind of a local statement. It's just describing it at one point. So these structures, because it's kind of a pinching inequality that they saturate, they're called extremely Ricci-pinched structures. Another interesting value is lambda equals 0. So closed G2-structure is called is called an eigenform if it's an eigenfunction for the Laplace operator. And that turns out, well, you can kind of see straight away from the equation that lambda equals 0. I guess you need to know that the Laplacian of phi is equal to d tau. So this thing is the Laplacian of phi, and then it's going to be a multiple of phi if and only if lambda equals 0. And these structures are kind of play the same role, or expect to play the same role in the Laplacian flow as Einstein metrics would for the Ricci flow. And then there's one more interesting value of lambda, and that's that the metric, the induced metric is conformally flat, implies that the structure is minus 1/8 quadratic. It implies more equations, but it in particular applies that it's minus 1/8 quadratic. And I'm not going to talk about it in this this talk, but I've classified these things in a paper I released in February. And it turns out that they're kind of incomplete unless they're flat. Okay, so these are kind of 4 interesting values of lambda that maybe kind of motivate this study of this general equation. And in particular, anything you can say about the general equation, you're going to say about any of these particular values. Okay, so the previous work that was done on this, it hasn't been that well studied. In particular, there are very, very few examples of any of these lambda quadratic closed G2 structures. So when Robert Bryant introduced these structures, he gave one homogeneous example of an extremely Ricci-pinched G2 structure. And interestingly, it kind of admits locally homogeneous compact quotients. So it has his example is homogeneous, and then it has a co-compact lattice that you can quotient down by. Yeah, and it's interesting because, you know, I'd say primarily the interest in extremely Ricci-pinched things comes from the compact case, because they're defined initially in terms of kind of conditions that should hold for compact manifolds. Okay. There was an ERP example due to Jorge Larret maybe 4 years ago. He defined on a solvable Lie group GJ, and this example was recently shown to admit compact quotients by Kath and Larret. In particular, this falsified a conjecture of Clayton and Ivanov that suggested that the only possible compact ERP G2 structures should be the quotients of Bryant's example. So there was it was discovered that there was another family of compact examples. Jorge Larret and Marina Nicolini have classified left invariant ERP G2 structures on Lie groups, and their classification contains this example. It turns out can be written as a structure on a left invariant group. And this example, of course, can. And they have 3 new examples that are distinct from these 2 as part of their classification. And they'll just say, in the course of my classification of closed G2 structures with conformally flat induced metric, I was able to get 2 examples each for these particular values. And they turn out to be incomplete. So this one is directly related to the conformally flat equation, and these ones are sort of constructed by analogy. Okay. So these are all the examples that existed as far as I'm aware. But there were a couple of extra results. So in Robert's initial paper, he proved that the only possible value for lambda actually on a compact manifold is lambda equals 1/6. And he also kind of gave structural results on the geometry of a compact example, like what would have to happen for a compact example. And then he proved that there were no possible examples for lambda equals 4/3. Which is kind of interesting. Yeah. Okay, so we were presented then with this quadratic condition, and it's a PDE system. So what can we say kind of just by looking at this PDE system? So I'm going to view it as a PDE system for a closed section of this space. It's a second order equation, like I said, because tau is first order, so therefore d tau should be a second order thing, and everything on the right hand side is first order, so it kind of describes second order behavior of this closed section. It's an overdetermined equation. So these closed sections phi, these closed G2 structures, depend modulo diffeomorphism on 8 functions of 7 variables. And the way to see that is to sort of say that locally my closed free form can be written as an exact free form, so it's d of some 2 form, and then kind of just do the counting based on that, and you get to 8 functions of 7 variables. Well, the quadratic condition is the vanishing of a section of a vector model of rank 27, from what I said before. So this thing is 27 equations for 8 functions, so it's kind of very overdetermined. Okay. And I'll say it's elliptic modulo diffeomorphism. What that means then, kind of, it's elliptic in the sense that its real characteristic variety vanishes. But modulo diffeomorphism, well, this equation is diffeomorphism invariant because everything here is an invariant of the G2 structure, so it can't be actually elliptic. It has to be elliptic modulo diffeomorphism. Okay, well, it's an overdetermined PDE system, so the kind of natural thing to do is maybe to study it from the point of view of exterior differential systems. A kind of differential systems theory, but unfortunately it's not involutive. And that means that the Cartan-Kähler theorem can't be used to prove the local existence of solutions without doing further work, such as prolongations. That's not that good a thing from the local existence theory. So let me explain where this non-involutivity comes from. Okay, now for any second order, for any closed G2 structure, the space of second order invariants turns out to be a vector bundle of rank 168. And it splits naturally into kind of G2 irreducible constituents of ranks 27, 64, and 77. So I'm going to call the resulting tensors that you get H, W64, and W77. The reason I've used W for these things is that these tensors that you get can be naturally identified with parts of the Val tensor. The algebraic space in which the Val tensor lives decomposes as a G2 representation into exactly a 27-dimensional piece, a 64-dimensional piece, and a 77-dimensional piece. And these tensors are exactly kind of the part of the Val tensor that corresponds to those G2 components. H also appears in the Val tensor, but it also kind of appears in the Ricci tensor as well. So there's something special happening for the curvature of a closed G2 structure. Okay, the lambda quadratic condition, what it does is it prescribes this 27-dimensional piece as a quadratic function of the components of tau. So the kind of once you have a quadratic closed G2 structure, the remaining second order invariants are exactly W64 and W77, these tensors. But by kind of applying the standard exterior differential systems machinery, kind of the method of moving frame stuff, you can show that the second order invariants must satisfy some extra equations. So it turns out there's 34 equations that contain terms of the form T times W64 plus T cubed, where T denotes the components of tau. And then 27 extra equations of this form. Now these equations are second order equations, but it turns out that in order to uncover them, you have to differentiate the structure 3 times or 4 times. So in particular, that implies non-involutivity, but maybe kind of a down to earth way of thinking of this is that there are restrictions on the 2-jet of a lambda quadratic closed G2 structure that are not algebraic consequences of the actual equation itself. So the equation itself describes H in terms of T, say. But these equations are completely algebraically independent of the lambda quadratic condition. And kind of this is the reason for non-involutivity. I should say that in Robert's initial paper, he essentially derived these equations, these first 34, and he asked the question, what happens if you make a new exterior differential system by kind of adjoining these equations to your initial one? Well, then that's still not involutive because exactly these 28 equations appear, which are new. You can do the same thing. You could say, look at the exterior differential system consisting of the quadratic condition, these 34 equations, and these 28 equations, but unfortunately, it's still not involutive. So you do this prolongation process, and it's not involutive. And actually, you can prolong 3 times, and you still don't reach involution. So from the point of view of exterior differential systems, from the point of view of kind of local solvability of this PDE system, this is kind of a very kind of nasty system. A natural question would then be, how many examples are there? We've already demonstrated a handful of examples. Maybe that's all. Maybe that's all that there is. So I kind of want to move into thinking about how to produce examples, how to maybe get some extra structure out of this. And to produce examples, you need you need to have an idea. So this idea is, in this context, is I call it special torsion. So just recall that the torsion 2 form was not just any 2 form, it was a section of this particular bundle, lambda 214, which was a vector bundle modeled on the adjoint representation G2. So if I take any element that lies in this 14-dimensional subbundle, I can kind of think of it as an element of G2, and I can conjugate it so it lies in a maximal torus. And if you do that, it's the following inequality becomes kind of very easy to demonstrate. Here, beta cubed is, we're thinking of beta as a 2 form, and beta cubed is just kind of wedge beta with itself 3 times. So we always have this inequality, and the guys on either end of this equality, so the ones that satisfy beta cubed squared equals 0, and the ones that satisfy beta cubed squared is equal to 2/3 norm of beta to the power 6, are kind of special. So the torsion 2, if the torsion 2 form kind of lies at either end of this inequality, I will say it has special torsion. So a closed G2 structure is said to have special torsion of positive type if the norm squared of tau cubed is 0, and it's said to have special torsion of negative type if the norm squared of tau cubed is equal to 2/3 times the norm of tau to the power 6. So these are kind of guys that live on the ends of these inequalities. And it turns out that these conditions, I've chosen to write them kind of at these because it's a very down-to-earth way to write them, but they're equivalent to the fact that tau has a G2 stabilizer isomorphic to the group U2. Now the different types, the positive type and negative type, are stabilized by different conjugacy classes of U2 inside G2. So they are kind of very different and have a different flavor. Here's a picture of kind of a root diagram of G2. Like I said, we could conjugate any of these 2 forms so it lies in a maximal torus, and you can draw the maximal torus because G2 is of rank 2. You can draw it on the plane, and you have that these special 2 forms are exactly on these kind of axes that you get in the root diagram. And then outside of these axes, you have the generic stabilizer for the 2 form, which is T2. Okay, so these special torsion conditions, you can see already that they're first order equations because tau is a first order invariant. So it's this first order condition on phi. And the reason that they're kind of useful to think of in these contexts is that these equations that must be satisfied here, saying that tau has special torsion means that these components of tau take a very special form, and these equations simplify massively under this assumption. So that's the reason that special torsion is kind of a useful thing to think of here. These conditions have a much simpler form if you assume already that your structure has special torsion. And then for the rest of the talk, I'm going to focus on lambda quadratic closed G2 structures that have under this special torsion assumption. So it's kind of an extra condition that I'm applying and hoping that everything simplifies a little bit. Okay. Are there any questions about this? Okay. I think this is maybe for people who aren't kind of really specialists, I think this is one of the key parts of the talk, these kind of special torsion conditions. I'm going to use them in the context of the lambda quadratic condition, but I think these will be interesting to study independent of the lambda quadratic condition. In particular, any question that you ask about closed G2 structures that might turn out to be too hard, you could ask for closed G2 structures that have special torsion of one of these types. In particular, you could try and classify homogeneous examples, or you could try and study, classify Laplace solitons under these extra conditions. Okay. But today I'm going to focus on lambda quadratic closed G2 structures with this special torsion condition. So there are 2 cases. There's the positive type and the negative type. So let's start with the positive type. So let's let M with a closed G2 structure phi be a lambda quadratic closed G2 structure with special torsion of positive type. Well, this is equivalent to the equation tau wedge tau equals 0 on M. Okay, but Bryant, Robert Bryant has shown that for any lambda quadratic closed G2 structure, the following equation must hold. So d of tau cubed is 3/7 times 6 lambda minus 1 times the norm of tau to the power 4 times the volume form. And we're not interested in the case where tau vanishes identically, because that's the torsion-free case. So we see already, if we're going to have this tau cubed equals 0, we better have lambda equals 1/6. So lambda equals 1/6, and we're in the extremely Ricci-pinched case. So already assuming positive type implies that we have an extremely Ricci-pinched structure. And furthermore, an extremely Ricci-pinched structure on a compact manifold must actually satisfy this, must have this special torsion condition. And this was one of the motivations for introducing this condition. And that's because of the following identities. So the exterior derivative of the norm of tau squared is 2/9 times star tau cubed. and the norm of tau squared is a harmonic function. So if we're on a compact manifold, the norm of tau squared better be constant, which then immediately implies that star of tau cubed equals 0, which implies that tau cubed equals 0, which implies that we have special torsion of positive type. So if you want to look for compact examples of these ERP G2 structures, you're already forced to look at positive type. Okay. Yeah. So I should say that our approach in general is going to be to study the geometry induced on the manifold by the torsion form itself. Well, how does that happen in this case? The assumption of special torsion of positive type implies that at every point of M, there's a coframe such that phi looks like the standard free form, and tau is just some constant multiple of this 2 form. The reason that tau is a constant is because of this equation. So we're assuming, again, that tau cubed equals 0. So that implies that the norm of tau squared is constant, which will imply that k is a constant instead of a function, possibly. Okay. Now, the collection of all the coframes in which phi and tau take this form is a U2 plus principal subbundle, the coframe bundle of M. So here U2 plus is just one of these, is a representative of one of these constancy classes of U2. So what is a U2 principal subbundle, the coframe bundle, is also called a U2 structure. So this torsion form tau kind of defines a new geometric structure on the manifold. And then you can look at the torsion of this U2 structure, which kind of proceeds in kind of general framework of G2 structures. And the torsion of this U2 structure is kind of heavily constrained by the various differential identities that must be satisfied by phi and tau. So you already know that phi is a closed G2 structure. The lambda quadratic, the ERP condition, implies that the derivative of the torsion form must be expressed in terms of the torsion form and phi. So you get these nice differential identities, and they turn out to constrain the torsion of this U2 plus structure. And it turns out that this torsion is a section of a vector bundle of real rank 27. The torsion of a sort of a general U2 plus structure in dimension 7 would be a section of a vector bundle of rank 119. So we already see that this is kind of a very special case, because 27 is a lot less than 119. And this torsion space is modeled on a U2 representation, because we're thinking of a U2 structure. And this U2 representation is this. So there's kind of a quintic, tensor sum kind of twisted by something, a quartic twisted by something again, and then just a kind of an element of C2. And then we have an element of R. So this R part of the torsion is exactly tau, because tau just takes values in a line under the representation of U2, whereas this A, S, and N, so I'm going to say that A is the tensor that you get by taking the torsion and projecting it to this component. Similarly, S and N are the tensors you get by projecting the torsion to this and this component, respectively. These things really kind of come from the U2 structure, whereas this part of the torsion comes from the torsion of the G2 structure, this 2 form tau. So let's let A, S, and N denote the resulting tensors on my manifold M. Okay. Now, the U2 action on the tangent spaces of M is reducible. So if I just think of U2 as a subgroup of G2, well, G2 acts on R7, so U2 is going to act on R7, and it splits R7 into R3 plus C2. Okay, and then therefore, if I apply that to the whole manifold, the tangent spaces will split as kind of P3 plus Q4, where P is modeled on this R3 and Q is modeled on this C2. And then it turns out that the equations that the torsion must satisfy imply that these distributions are actually integrable. And this allows us to interpret these tensors, this AS and N tensors are kind of interpreted in terms of these distributions. So for example, A is the second fundamental form of the Lees of Q. S is the second fundamental form of the Lees of P. And finally, the torsion form itself and the metric will define an almost scalar structure on the Lees of Q. So these 4-dimensional Lees will get an almost scalar structure. And the tensor N is simply the Nine-House tensor of these Lees. So these 3 tensors that you get have a very nice interpretation in terms of the geometry of these 2 distributions. And finally, you can kind of ask most simply what happens, what if all these tensors vanish? Well, it turns out a structure with all these tensors vanishing must be locally equivalent to Robert's initial example, the kind of original example that he produced. Then motivated by this, you could maybe ask, well, what happens? This is what happens if they all vanish, but what happens if all but one vanishes? So I'll say that M is of type A. If this tensor A is the only non-vanishing tensor out of these 3, similarly type S, if S is the only non-vanishing tensor, and N if N is the only non-vanishing tensor. And I'll just study these structures under that extra condition. Well, for types A and N, you get Weierstrass formula. So the structures of type A, so again, that's the structures where S equals 0 and N equals 0, turn out that you can describe these explicitly in terms of a single holomorphic function. So there's a Weierstrass type formula for these structures, which basically goes like this. If you give me a holomorphic function, one complex variable, then I can construct an ERP closed G2 structure of type A. And in particular, if you give me two different holomorphic functions, I'm going to get two distinct ERP closed G2 structures. And conversely, every structure that's of type A can be locally described in terms of this holomorphic function. So this is quite nice. I wish I had space or time to really write down the formula, but it's a little bit intricate. It's nice in that then this produces already kind of infinitely many local examples of ERP G2 structures because there's infinitely many distinct holomorphic functions. One problem is that there are completeness issues. So there are issues here. So when your holomorphic function has poles or zeros, you get completeness issues with your structure. So I don't think you can actually get complete examples with this procedure, with this Weierstrass type formula. So that's what happens with type A. For type N, it turns out that every structure of type N arises as a bundle of compatible metrics over some four-manifold X that carries this kind of S1.SL2C structure of a certain special type. So an S1.SL2C structure is basically a kind of a holomorphic volume form that's defined up to phase. And if this structure satisfies some extra conditions, then the bundle of metrics that are compatible with this holomorphic volume form up to phase, it's a 7-manifold. It's a fiber bundle over X with fibers isometric to hyperbolic 3 space, and it will carry an ERP G2 structure of type N. Unfortunately, well, so a subclass of these structures admits a Weierstrass formula, similar to how it goes for the type A case, but in general, it's a little bit mysterious. The local existence theory is also hard for these things. So I know the subclass exists and has the same kind of local generality as the type A structures, but I don't know if every structure must be of this subclass or whether there's other structures. That kind of remains mysterious. Okay, so that's type A and N. Again, these structures of type N have completeness issues. So you'll get infinitely many local examples, but I don't think that you can get a complete example. Certainly not a compact example out of this construction. Okay, but what's a little bit more interesting is the structures of type S. For the structures of type S, these four-dimensional leaves of this distribution Q. So Jason asks the question, is there a way to see the surface for the type A examples, i.e. the one complex variable? It's a little bit harder. So the surface is related to this P3. So it turns out that when you're in the type A example, what happens is that the tensor A, like I said here, is a symmetric quintic, kind of twisted by something. And it turns out that when you're type A, the symmetric quintic must actually have a quintuple root. That follows from various differential identities. So it has a quintuple root, which means that this root kind of defines a special direction. And this special direction is in the P direction. And then the surface kind of is the remaining directions in this P, the remaining two directions in this P, the orthogonal complement of this special direction. So you can kind of see the surface in that way. What's maybe a little bit harder is it's maybe a bit harder to see that the surface, I think it should be possible to see the surface as some submanifold of some ambient space, but I haven't been able to come up with a reasonable way to do that. Hopefully that's a reasonable answer. The surface basically comes because the tensor A has a quintuple root, and then you take the orthogonal complement in P, and that gives you the two directions that make up the surface. All right. So these structures of type S, these four-dimensional leaves of Q are flat co-associative fibration of M. So it turns out that the condition that A and N vanish imply that the curvature tensor of any of the four-dimensional leaves of Q completely vanishes. So we're in a very special case. In fact, we're in a case that's been studied before. Baralia has studied kind of general closed G2 structures that are fibered by these flat co-associatives. And he shows very interestingly that they're locally equivalent to space-like three-dimensional submanifolds of this pseudo-Euclidean space. So space-like just means that if I take my three-dimensional submanifold and restrict the pseudo-Euclidean metric of signature 3,3 on this space, then I get an actual Riemannian, a Riemannian structure on my three-dimensional submanifold. Construction kind of goes like this. So if I have my space-like immersion of a three-manifold into this space, I can think of this space as lambda 2 of R plus with the intersection product. It's kind of the wedge product, inner product. Then the G2 structure associated to this immersion is simply given by, you take the volume form associated to the pullback metric and add du. So here, u maxed into the space of two forms. So du, I can kind of lower index and I'll get a TB direction, and I'll have the lambda 2 here, and I can make that into a 3 form. And the manifold M is just simply B times R4. Okay, so this is how the G2 structure is constructed. If I start with one of these, and he shows that conversely, if I had a closed G2 structure that's fibered by the flat co-associatives, it must locally be of this form. Okay, and furthermore, he proves that if phi is going to be torsion free, then that's true if and only if this immersion is maximal, i.e. the mean curvature of this immersion vanishes. So maximal here, because we're in the pseudo-Euclidean space, that would be called minimal if this was a Riemannian manifold, but it's called maximal here. Okay, so you can ask, well, that's what happened for torsion-free structures, but what happens for the ERP structures? So in the ERP case, you get an analog of Braille's results. The analog is that instead of having a maximal submanifold of R3, 3, you actually get a maximal submanifold of this quadratic of vectors of norm -1 in this space. So it's kind of, you go into this 5-dimensional quadratic and you have to be maximal there. Okay, so this 5-manifold X is the negatively curved pseudo-Riemannian symmetric space, SO33 mod SO32, that has signature 3,2. So space X submanifold is just a submanifold where you get a Riemannian structure again, and again, maximal implies that this is equivalent to this vanishing of this mean curvature vector. Okay, and then, so it turns out that every previously known example on that list, so all of Loretti-Nicolini's examples appearing in their classification, say, turn out to be of this type S. And then for each of these examples, you could calculate the corresponding maximal submanifold of X. Okay, as a basic example, Bryant's example, this corresponds to a totally geodesic hyperbolic 3 space inside this 5-dimensional manifold. And you get kind of, for each example in the Loretti-Nicolini lift invariant calculation, you're going to get a homogeneous maximal submanifold of X. Okay, the structures of type S are also interesting from the point of view of the Laplacian flow. So if I have a U2 plus structure that's ERP, and I flow it using the Laplace flow, all that happens is that the P directions are fixed, and the Q directions move at a speed exponential in time. I'll just say that this computation was done independently by Anafino and Alberto Rufero. And it's kind of, once you have the U2 plus structure, the Laplacian of the 3 form is exactly d tau. So d tau takes a very special form, so it's not too hard to do this computation. Takes a little bit of work. Now, because of this, because the Q directions expand at speed exponential time and the P directions stay fixed, well, if the Q directions are flat, you somehow expect that you can kind of rescale them using a vector field. And so this maybe makes the following theorem a little bit unsurprising. It's that the universal cover of an ERP U2 plus structure of type S turns out to be a steady soliton for the Laplace flow. So a steady soliton is just a solution to the Laplace flow that just evolves just by diffeomorphisms. It doesn't scale or anything. It's kind of a fixed point for the flow up to diffeomorphism. Now, Loretti-Nicolini had noticed that all of their examples were steady Laplace solitons. So this, given that all their examples are type S, this theorem kind of explains this observation. I'll just say Laplace solitons are solutions to the Laplace flow that evolve by scaling to diffeomorphisms. With closed G2 structures, a Laplace soliton if and only if there's a constant C in a vector field X, so that it satisfies this equation. And both the Laplacian of phi is equal to d tau. So you can kind of see that this equation is very much of the same form as the quadratic equation. Again, you're specifying d tau. So it takes a very similar form, and it's maybe unsurprising then that there's a relation between Laplace solitons and quadratic G2 structures. Okay. So with this understanding of type S structures, you get some very nice things. The tensor S is identified with the second fundamental form of this immersion. And if you want to generate new examples of ERP G2 structures, you could kind of put extra conditions on S. You could study immersions such that S has extra pointwise symmetries. One result, you kind of study these things, and one result that you get is the existence of a complete inhomogeneous ERP G2 structure. So all the previously known examples had been homogeneous, but and in the type A and N things, I was able to construct examples of inhomogeneous incomplete ones, but by doing this, you're going to actually get a complete inhomogeneous G2 structure. It turns out to be cohomogeneity 1 under the action. Well, the corresponding space like maximal submanifold is cohomogeneity 1 under the action of SO2-1, and you can describe it completely explicitly. Okay, so I think this is important enough to record kind of as a theorem. It's a kind of important example that shows that ERP G2 structures don't just have to be locally homogeneous. Okay. Now this is the seminar on geometries with symmetries, and I've just kind of tied it in a less symmetric example. So I'm going to make up for that by classifying all the homogeneous examples, so all the examples that have the most symmetries. So the following classification theorem kind of extends maybe Jorge Loret and Marina Nicolini's classification of the left invariant structures on Lie groups, because obviously you could have a homogeneous space that wasn't a Lie group, wasn't equivalent to a Lie group. So it turns out when you do this classification, all you get is the same 5 examples that appear on Loret and Nicolini's list. So you have Bryant's example, Loret's example GJ, and then kind of Loret and Nicolini's examples GM1. You get these 2 examples, these 4 and 5, these examples with 8-dimensional symmetry group. But it turns out that they're equivalent to Loret and Nicolini's examples already. So you don't really get anything new, but you do get kind of interestingly that these things have an extra symmetry, have an extra dimensions worth of symmetry. The proof is not too hard once you kind of have all the torsion and everything. The first step is to show that a homogeneous ERP G2 structure has special torsion of positive type. And this just follows from this identity, because if it's homogeneous, then the norm of tau squared better be constant. So we get the tau cubed vanishes, which implies a special torsion of positive type. Next, you use Loret and Nicolini's left invariant classification to reduce to the case where you have a non-trivial isotropy. So kind of G mod H, where H has dimension at least 1. Then the representation theory of this torsion space, the space where A and S live, implies that if you have a homogeneous example with non-trivial isotropy, then it must be either type A, N, or S. So only one of the tensors could exist. Next, I've already analyzed the structures of type A and N, and it turns out none of them can be homogeneous. So there's no examples there. And then for type S, the non-trivial isotropy implies the existence of symmetries in the second fundamental form. And then you can just kind of attack that head on with the method of moving frame and classify exactly what the possible examples would be. And you get exactly these 5. One interesting thing, I said that these extra symmetries here are useful. So the presence of additional symmetries is noteworthy. Well, this group GM3 that appears in their examples, it's not unimodular, so you definitely couldn't get a co-compact lattice there, and you can produce compact examples in that way. But the G2 automorphism group is larger. It contains this group, where SL2R acts as 2 copies of the standard representation, and this R acts kind of scaling one of the R directions and inverse scaling the other directions. And it turns out that this G2 automorphism group does admit co-compact lattices that you can get kind of from the theory of arithmetic subgroups of SL2R. So in this way, you get a new example of a compact ERP G2 structure, which is the third kind of, I guess, the third family of examples that would appear. So I think I'm kind of running out of time a little bit. Have run out of time maybe. So I'll just very quickly say that you can study the negative type in the exact same manner. These closed G2, lambda quadratic closed G2 structures with special torsion negative type. You can make a very similar study, and you just get this theorem. So in particular, it turns out that the induced metric must be incomplete, which was not the case before. And the constant lambda has to be equal to one of these 4 possible values: -1, -1/8, 2/5, or 3/4. And furthermore, for each of those lambda values, there exist infinitely many examples. So you do get examples for each of these, and infinitely many. But unfortunately, they're all necessarily incomplete.
Gavin?
Yeah.
May I ask you something?
Yeah.
Can this negative type be also characterized by tau having 2 eigenvalues of multiplicity 2?
Yeah, exactly. Yeah.
Okay.
Yeah, and that gives you this U2 stabilizer because the eigenspace for those 2 eigenvalues is 4-dimensional, and the kind of U2 acts on that 4-dimensional C2.
Thanks.
Yeah, exactly. So for these examples, maybe because of the incompleteness, it's a little bit less interesting. I'll just say the necessarily of the form r plus times n, where n is just the manifold where this norm twice squared equals 1, and the incompleteness comes at 0 in this r plus. You can say a little bit more. I'll just say that the possibilities for n kind of all take this form. So it's T2 times a Calabi twofold, the twistor space of a Calabi twofold, a T2 bundle for a particular hyperkähler four manifold, or the twistor space of S4 or the twistor space of CP2 kind of are the most basic possibilities for n. And then I'll just say finally then that I don't really have time to say this, that by looking at how the G2 structure looks in each of these cases, you could make an ansatz that allows you to construct complete inhomogeneous gradient steady solitons, the Laplace flow, kind of large families of these, infinite families of these. And I think that these are the first examples of inhomogeneous Laplace solitons. And I think they're kind of the first examples of Laplace solitons that are kind of explicitly labeled as gradient solitons. I'll just maybe emphasize that these things aren't lambda quadratic. They just arise from an ansatz that's kind of based on the negative, special torsion of negative type examples that appeared in the lambda quadratic case. Okay. Thanks for your attention. Thank you.
Thank you, Gavin, for a wonderful talk. Are there questions? Questions? Okay, if there's no questions, let's thank the speaker again.